Okay, so to measure atmospheric pressure, what we do is you can have liquid mercury, which is a very dense liquid, and what we can tell is that if this is a vacuum, the air pressure is pushing the mercury up a distance of 29.92 inches of mercury, which that is used in American weather systems, but not so much in problems. If you're at sea level, it should push it up 760 millimeters of mercury. That's how far up the atmospheric pressure should push mercury into a tube. If we're measuring a gas, a sample of gas, so let's say that we have the gas in here, and it's pushing in this mercury, and here the atmospheric pressure is pushing, we see that the atmosphere is winning. So what we would do is take the atmospheric pressure, we would subtract this many millimeters of mercury, and we would have the pressure of the gas, because it's less than the atmospheric pressure by that much. Conversely, if we had a gas and it's pushing down here, and atmosphere is pushing down here, the gas is kind of winning by this much. So we take the atmospheric pressure, add this height to it, and that would be the pressure of the gas in the barometer. That was actually called a manometer. All right, some units of pressure that are commonly used, and there's a lot of them: atmospheres, torrs, millimeters of mercury, pascals, and kilopascals. PSI is not really used that much except in the US for like tire pressure and that kind of thing. If we're going to convert, we just go ahead and use dimensional analysis. So let's say we have this, we want to get atmospheres. We see 760 millimeters is an atmosphere. So I'm going to go 760 millimeters of mercury is 1 atmosphere. And to find atmosphere, it's supposed to be a 1. I'm going to go 525 divided by 760, and that will be my atmospheres of pressure. Let's say I wanted to go to atmospheres to torr. Well, I would take atmospheres. I'd go up here. 1 atmosphere is 760 torr. And so now I would take 3 times 760 and get my pressure in torr. Boyles Law is a look at what happens with volume and pressure if I keep temperature and moles of gas constant. And what we find, not really rocket science, is that if I decrease the volume, all right, so I've got a pressure and a volume, let's say a balloon, but I squish that balloon and I try to make it tinier and tinier, what's going to happen to the pressure? Well, the pressure is going to go up because this is going to be constant. Whatever it is before is going to be afterwards. So the two are inversely proportional. As one goes down, the other has to go up. And just think about squishing a balloon. This would be the graphical analysis of Boyles Law. As we take this volume and go down and go down and down, the pressure is going to go up, up, up. Now why is it flatlining here? Well, the gas is liquefying. It's not going to stay a gas if you keep it under a lot of pressure. So an example here, I'm going to take a 1.5 liter sample. That's our V1. Our 56 torr is P2 or P1. I'm going to go to P2, 150 torr, and we don't know V2. That's the question. Now the thing about this is, along with Boyles Law, as long as you have these the same unit, you're fine. So if this is torr, this has to be torr. If this were millimeters of mercury, this would have to be millimeters of mercury. Now those two are the same, so that's pretty easy. But if this was atmospheres, you'd have to change that to atmospheres. They have to equal. And when I go to solve this, which is basically going to be 1.5 times 56 divided by 150, when I go to solve that, it will be in liters because this was in liters. All right, Charles' law talks about volume and temperature keeping pressure and amount of gas constant. And again, this isn't really rocket science. We know that if you take some balloons out in a super cold winter day, the volume, they shrink. Bring them back in, temperature goes up, the volume's going to go up. These are directly proportional as it goes up. I'll show you an experiment that Charles did. He basically took a bunch of gases, cooled them down. At some point they liquefied, so he had to extrapolate the data, but they all converged at this negative 273. And Lord Kelvin took up on the idea and decided to make the new temperature scale start absolute zero at 0. So instead of making this negative 273, Kelvin said, hey, let's just make that 0 Kelvin. Alright, so here is one of the examples of what Charles did. These are, perhaps different gases that he used. I don't know what he used exactly. But he found that they all came down to negative 273 degrees Celsius, or 0 Kelvin. Turns out we're going to have to do all of our gas law problems in Kelvin. So if you have a degree Celsius, simply add 273 to it, all right? You have to do that to get it into Kelvin temperature. Absolute must. You can see here, if I put a temperature of 0 degrees below, here it's an undefined problem. So this is Charles's law, V1 over T1 equals V2 over T2. So let's take a look at this one. We've got a 2-liter sample, V1, collected at 298, T1. It's cooled, T2, and we want to know what's V2. Okay, so we're going to go 2 liters over 298 Kelvin is going to equal V2 over 278 Kelvin. We're going to cool this down. So without even doing any math, we know we're cooling this down, so that we know the volume's got to be less than 2. So I'm not going to actually calculate it for you, but please do that so you feel like you know what you're doing here. So we're going to go 2 times 278, we're going to divide it by the 298, and you should get your volume in liters. Alright, now the combined gas law is actually all you need. You don't need individual Charles and Boyles, because, well, what if your pressure is kept the same? Well, just get rid of the pressure. Say they don't change. They say 2 atmospheres, 2 atmospheres. Okay, well, put it in or cancel it, whatever you want. Let's say the temperature stays the same. 298 Kelvin, 298 Kelvin. Either cancel it or, go ahead and keep it in there. But you don't really need Charles or Boyles. You really just need a combination for those. We're going to use these problems when things are changing. We're going from one pressure to another pressure, one temperature to another temperature, one volume to another volume. So definitely read the questions carefully. All right, so let's just go through here. V1, 5 liters. T1, P1. It's cooled to, okay, T2. Pressure D, okay, this is P2, and we're looking for V2. All right, so we're going to go V1, P1 over T1. Now, be careful. Don't just use 22. Make sure you change that to Kelvin. It will not work otherwise. All right, we're going to, we don't know V2, but P2, we're going to go down to 2 atmospheres. And we're going down to 1 degree Celsius, so 274 Kelvin. Okay. All right, now to solve for V2, again, make sure you do this. I'm going to cross multiply. I'm going to take that times that, and I'm going to divide it by these two numbers. All right, so we're going to go 5 times 3 times 274. Going to divide it by, let's see, 295. That's 295, right? Times 2. Now when you do this on your calculator, make sure that you parentheses these up. If you go 5 times 3 times 274 divided by 295 times 2, it won't do it right. You have to put brackets around here or parentheses.